Hello, statistics student. This video is for chapter 7.2, central limit theorem for sums. So this is not a very popular central limit theorem. So if you Google central limit theorem for sum, I don't think you find a lot of hits. Most of the central limit theorems are for sample means. And we already know that sample mean is normal. So if your n is greater than 30, no matter what you start off, then you would have a normal distribution of mu and sigma divided by square root n. The standard deviation is smaller. What happened is we're trying to see, instead of finding a sample mean, we just add them together. We want to see the sampling distribution of sum of x, represented by sigma x. That means add all the samples together. So that means, so you can say, oh, I have some real distribution or any distribution of x. I get a sample, but I just add them together. I don't divide it by n. I do a lot of them. Another one, and I do a distribution. So it turns out that this sum is, this is the sum. So all of the sum, we don't have a symbol for it. We just say sum of x, sum of x. So these would be normally distributed with the mean, not mu anymore, but n times mu. And the standard deviation is sigma not times n, but sigma times square root n. Okay, so this is an extension of the central limit theorem. It's useful to solve a lot of work problem. So the central limit theorem notation would be mu of sum is equal to n times mu. Sigma of sum is sigma times square root of n. Okay, so this applies to all distribution, any distribution of x, but if x is normally distributed, n greater than 30 is not needed. It's just like the central limit theorem for sample mean, n equal to greater than 30 is only required if you don't know the distribution. If x is normally distributed, any n would work. And also the sample must be a simple random sample. So let's do a few examples on this. The reason why we introduce this is exceedingly useful to solve problems that involve adding samples, that sum of samples. So if you have a boat, like traveling, you don't have you are worried about overload, right? So but then everybody's weights is distributed, is not the same. So how can you guarantee that the boat would not be overloaded? Do you use the mean of the weights to make sure that it's not overloaded? A better way is to use the central limit theorem for sum to model the distribution of the sum. Okay, so a quick example would be like this. An unknown distribution has a mean of 45 and a standard deviation of 8. A sample size of 50 is drawn randomly from the population. So 50 is really large. So of course we can use the central limit theorem for sum, right? So then can the central limit theorem for sum? Yes, right? Because n is equal to 50 is greater than 30. So CLT for sum apply. So it's just the same as what we have. B, find the probability the sum of the 50 value is more than 2400. So let's find out what this sigma x would be, a normal distribution, and we say is n mu and square root n sigma, right? So what is n? N is 50, and then we have 45, so that would be n 50 times 45, and square root of 50 times 8. So let's calculate it. So that means it's normally distributed with the mean of 50 times 45, which is 2250. So our normal distribution has a mean of 2250. And then we can do square root of 50 times 8, because the original one distribution is 56.56. So sigma equal to 56.5685. 56.5685. And we want it to be more than 2400. So how many standard deviation is like, I think more than 2, right? So it's really low. So let's do the write down first 225056565, and we want it to be over 2400. Use the online calculator. Here, the mean is 2250. Standard deviation is 56.5685, and we want it to be above 2400. Recalculate 0.004. So it's really rare, right? So we would say probability of sum of x is greater than 2400 is 0.004. It's a very rare event. So if you have 50 people, if this is boats, and 2400 is overload or is the low limit, then this is good because it's very rare to happen. So this is what happened in example 2. We are not looking at the boats, but looking at an elevator. So when you look at the elevator's low weight limit, so this elevator has a maximum weight limit of 5,000 pounds or 27 passengers. Assuming that adult males have weights that are normally distributed with a mean of 189 and a standard deviation of 39. Now, when we look at safety, we usually look at males because their weight is higher, and it's possible that an elevator has all males. And, if they have meetings or if it's a group that go out to a trip or something, this is happen. So you can't just say that, oh, well, the elevator is used by children and female also. No, for safety purpose, we use the population that has the highest weight, mean weights. So the mean is 189. I'm going to write it down. And the standard deviation is 39. So now you allow 27 people to come in, like, so can the 27 passengers weight be normally be modeled by normal distribution? Yes, because here the distribution is normal. They say assume that they are normally distribution. We'll say yes, because given that we were given that we don't know, usually weight is not normal. Our weight is normal. Now, even if it's not normal, I think you can still do it because 27 is quite close to 30. If yes, what is the mean? So the mean would be n times the mean, would be 27 times the original mean, which is 189. The standard deviation of sigma x would be square root of 27 times 39. So let's calculate these two numbers. 27 times 189, I have it is 5103. Would it be a problem? We have the weight limit of 5,000. And then this is what? Square root of 27 times 39 is 202.6499. We can round it to 65. So does this elevator appear to be safe? You would want to know what is the probability that sum is greater than, yeah, so it's 5103. But your limit is that, right? Your limit is 5,000, which is actually below the mean. So all these would be overloaded. I think it would be, right? No, what happened? So I think it would be. So let's look at how to do this. We would put in the calculator. The mean is 189 times 27 is 5103. The standard deviation is 202.6499. And we want it to be above 5,000. It's more than a half, right? So 0.6944. So 69% equal to 0.6944. Should they allow 27 to come in people to come in, they should not, because it is not safe, right? So you would say here that it is not safe. Does not appear to be safe. So this is likely to not unlikely. So that means there's if they're all male come in, a group of all male comes in, it's very likely, it's not unlikely. So it's likely to happen for 24 male. So it's not safe. Let's look at one more. A passenger load for water taxi, so this is a boat, is 3,500 pounds. Assume weight of passengers are normally distributed. So here, weight is normally distributed, so we don't have to worry about the sample size. So the sample size now is they want to allow 20 people to go onto the water taxi. The weight of the passengers are 774 pounds with a standard deviation of 21 pounds. Can the sum weight be modeled by central limit theorem? Yes, because weight is normally distributed. If they don't say anything, you cannot. So set this up. What is the mean? Or normal distribution has mean. Mean is n mu, right? So is we have 20 times 174. So that is 20 times 174 in the calculator, 3480. What about standard deviation? Standard deviation is sigma of sum of x, that is square root of 20 times the original 21 sigma. So square root of 20 times 21, and then round it to 93.9149. So 3480 93.9149. So let's determine the probability that they will exceed 3,500 pounds. So 3480 is the mean, so it's actually quite close. So 3480, and the standard deviation is larger, 93.9149. And we wanted to see when it is going to above 3,500. Recalculate. It's 4159. So say probability of x greater than 3,500 is 0.40 4157. It's not unlikely, so it will happen. So it's actually like almost 41% chance. 3480 sigma is 93.9149. So this is not very good. So in your 45 is really actually close to the, so you can tell that it's just 40% chance. So it's not safe. It's not safe. When it is not unlikely, then it's not safe, because it's likely to happen. Okay. So I'm going to talk about normality assessment in next video.